Alright, hello kiddos. Welcome to Mrs. Kaufman's science videos for the home learners when you don't have the money for a magic school bus. Alright, so what we're talking about today is sound. So you guys might have a piece of paper already at home, I hope you do, that has all of this information on it. We're going to break down sound, go into a little bit of like, what does it mean? I know your paper has molecules moving in a longitudinal waves, but that probably means absolutely nothing to you. So we're going to fix that today. As I said, sound is molecules moving in longitudinal waves. So what does that mean? Well, when we look at the picture that I drew you, I gave you guys some stuff of some really dense areas, and then some spread out areas, and then some really dense areas, and then some spread out areas. And it kind of goes that whole way. And I said that the really dense areas, these guys were called compressions. So I'm just gonna do that. So compressions. Whereas these wide guys, these are called rarefactions. Rarefaction. Okay? Alright, so I actually have a little video that it should let me show you guys what this looks like in motion. So let's see what we get here. Alright, so what you're seeing here is you have a wave, a transverse wave, what we normally think of in waves, going like this, following down this slinky. Okay, so as we shake the slinky, the wave goes through it. A longitudinal wave is the same thing. As we push the slinky, that compressed part goes through it. So when we look back at our drawing, let's get back here. Okay, when we look back at our drawing, when we have those clumped up parts, and you guys can see it in the dot drawing that I put on your guys' types of energy sheet that you took home, you can see that compressed part is when a bunch of particles, a bunch of molecules are all stuck together. So they're sticking together. There's another video I want to show you guys as well. Alright, so let's zoom out and take a look at it. Alright. So up here, I have a video with particles in it. So the movement is the same movement as it was in our slinky. The slinky itself isn't exactly moving down the line, it's just compressing, and that compressed part is moving down the line. So when we look here at let me get my little pointer up here. Okay, when we look here, we can see the wave is this compressed part that goes across. Okay? So we have compressions, and the in-between spaces, are called rarefactions. So, but when we look just at one single particle, one molecule of, say, like air, okay, we can see that it's not really actually traveling all the way down. The start of your slinky doesn't move down to the end of it. That's silly. It just passes along that energy. And so sound energy is that movement of molecules in the longitudinal wave thing. So we have, see this particle, and he bumps into those, which bumps into those, which bumps into those, which bumps into those, keeping this set of newly forming squished areas and thin areas in between. So when you say we make a noise, okay, when you have that noise starts shaking, it runs into the air around it. So me talking. While I'm talking, I am moving air from my lungs out of my body. That air is bumping into more air, which is bumping into more and more and more and more, until it gets to the end, or in this case, my microphone. So when you guys hear the sound coming out of your speakers, what you are hearing is those speakers. If you guys have ever looked inside a speaker and seen like that weird like circular kind of drum shape thing, that's literally what it's doing. The speaker is hitting the air making these patterns. And these patterns then go hitting air, hitting air, hitting air, hitting air, hitting air, until it gets to your eardrum. Your eardrum can take those sounds and turn that into what we think of as sound when we're hearing. So let's look at another example. So if we scroll up here, so this picture shows a tuning fork. So a tuning fork is a specially Y-shaped piece of metal that we use to produce a specific tone. What happens is when we hit those tones, the tuning fork, the ends of it will start shaking. As the tines of the tuning fork, the top of the Y part, start shaking, when they shake outwards, it causes all of the air next to them to be pushed away. This causes that compression area where all of them get squished into that one thing. But the tuning fork goes both ways. So you have it pushing out, making compressions, but then pulling back in towards the middle to make the rarefactions. This is the same thing that's happening if you you play a guitar and you pluck the string, and the string vibrates back and forth. It's making those compressed areas and rarefaction areas. So, for example, I'm going to show you guys a video of a piano. So, what you guys are seeing now is the inside of my piano. So, you can see that there are strings right in here, okay? And these guys are some hammers. So, I'm going to hit the string. Go a little bit lower so we can see it. Okay. So what you see in this video is the hammer hitting the string, and when it hits the string, that string vibrates, and it vibrates into the note that we hear. So maybe you're wondering, and you're like, but Miss Kaufman, how do we get different notes? I know all of those different strings can give different notes, but how does that work? And I would say, good question. In order to answer that, we're going to have to talk about a couple of words that we use to describe sound and waves in general. So the first word is amplitude. So amplitude is the intensity of a sound wave. So when we're talking about sound waves and we say, hey, this thing has a super high amplitude, we could also say that this thing has a very large volume. Okay? So you're listening to your music, you're like, man, I can't hear it, I gotta turn up the volume. You are turning up the amplitude of that sound, okay? And when we look at a picture, the bigger the amplitude, the taller the sound wave will become. But we don't need just amplitude, right? It's not just like all music is the same note all the time, just different volumes. We need to take into account what's called pitch. So, here's pitch. So, pitch depends on the frequency. And when we're talking about frequency, we're talking about how many waves are fitting into a second. Okay, so pitch depends on the frequency. So we can have things that are low pitch, okay? And we can have things that are high pitch. So low pitch might be like the rumbling of the garbage truck outside. It's the deep tones, okay? Boys have a lower pitch voice than girls do. So a high pitch might be like somebody scratching on the whole, nails on a chalkboard thing. That would be a high pitch noise, a high noise. So you can have low pitch noises that are very loud, or you can have low pitch noises that are very soft. The same goes for high. You can have loud high-pitched noises and soft high-pitched noises, but that doesn't change the actual note that they are. So if we go back to the piano, we can say that these notes, those are all low notes, versus we could say we have high notes. Okay? So the first set of notes, those would be low-pitched notes, versus the second set of notes would be high-pitched notes. In terms of frequency, humans can hear from 20 hertz, we'll talk about hertz in a second, to 20,000 hertz. Okay? This is also known as 20 kilohertz, because remember, kilo means 1,000. So we would read this as 20,000 hertz. Okay? So that means that anything that would be above what humans can hear is called ultrasound. So that means it's bigger than 20,000 hertz, 20 kilohertz. Okay? Whereas infrasound, that's sound that we can't hear because it's too low. So that would be less than 20 hertz. So for example, dog whistles that you can whistle into but humans can't hear it, but your dog can, is because that is ultrasonic. It is above human hearing. But dogs can hear above 20,000 hertz. Certain whales and stuff, when they make their sounds that go through the ocean, those are so low that we can't hear them. They are below human hearing. They are infrasound. They are less than 20 hertz. So we actually have ways of using both ultrasound and infrasound. So the first way you guys might have been like, oh, ultrasound, I know what that is. That's when, pregnant mom goes in, gets the picture of her baby, okay? This wand creates ultrasonic waves that go in, hit the baby, and bounce back, and then get read by the machine. The same thing works with infrasound, but we use that just like whales do in the ocean. We use that to figure out, hey, what is below us? So people that do fishing, they send out the sound wave, an infrasound. It strikes the fish and gets echoed back to the boat, which the boat can then read, hey, there's a big thing down there, whether that's a bunch of fish or a rock or, submarine. Okay, submarines do the same thing. That's how they navigate around without actually looking outside. They use sonar to get a picture back. So if we put all those pieces together, we can kind of look and see a diagram of how a wave works. So in this diagram, we have a wave. It's this orange piece that goes up and down. Okay, and we know a few things of the wave. We know how tall it is. So we go from the midpoint, we say it's this tall. The waves get to this tall. So this might have, if we said let's see here. If we said this was low volume, and this was medium volume, and this was medium volume, and this was high volume, we could say that, okay, yeah, this volume is probably little over medium, okay? So when we're talking about the highest point in a wave, we call the highest point the peak, okay? So if you hear me talking about the peak of a wave, I'm talking about the highest point. The lowest point, on the other hand, is called the trough. I know it's a funny English word, but it's trough, okay? So a wavelength is just the distance we say that is between 2 points, okay? So one whole wave is from the point here to the point here, the exact same point on the wave. We could also do it from peak to peak. So I'll grab my yellow here. So if I said I want to go from this guy to the next peak, which is this guy, okay? That distance, all of him, is one wave, okay? So that's our wavelength, how long one wave is. When we're looking at frequency, we're asking, okay, so how many wavelengths, how many of these waves fit in 1 second? So if we say, well, this whole thing, let's say from here to here, is 1 second, okay? This guy is 1 second. Okay? We could see there's 1, 2. Oh, okay, well there's 2 waves per second, so its frequency would be 2. Okay? If I said, well, hey, no. Only, let's undo this guy. Okay? So if I said, no, only here to here is 1 second. Okay? Well, then I'd be like, oh, well, that's only half of a wavelength. So I guess the frequency would be 1/2, because only half of a wave goes through in a second. Now, something neat happens, though, to the waves when they go through different things. So if you've ever tried to hear stuff underwater, you could actually try this at home if you have access to any swimming location or even just a tub at home. You can try this at home. Try banging things underwater and seeing how they sound differently above water versus underneath water. So now that we know what a wave looks like, let's talk about those units. So the units that we mostly use in sound, and there are some others, but we mostly use decibels and hertz. Decibels is for our volume or our amplitude. Okay? Amplitude. Okay, this is how loud things are. So, for example, here we have a picture of how many decibels is what thing. Okay, so if we look here and we see that we have whispers. Whispers are around 30 decibels. Okay, a quiet room around 40. So when you guys are actually taking a test, I've actually measured how loud you all are. And you're right around 40, 45. Okay, at 50 decibels, okay, we have like light rain. Okay, then we start to get into some that are louder. So we have like a dishwasher. If you were standing right next to a dishwasher or a vacuum cleaner. The vacuum cleaner is pretty loud. When you guys are talking, you guys are about the same like volume level as a vacuum cleaner. It's real fun. Okay? An alarm clock or a busy street, we're getting up to 80. So past 80, we're getting into the danger zone. Okay? This can result in permanent hearing loss. So these are things like using the lawnmower or power tools without ear protection. We have things like a snowmobile or a chainsaw, a bass drum, loud music, remote control airplane. So your loud music, guys, if I can hear your music, you are definitely in this extremely loud category at your ears. Okay, if I can hear your music, outside, or if I can hear your music like from across the room, then you guys are definitely getting into the painful, very damaging areas. So the issue with the decibels is that anything in the danger zone, the farther up you go, the faster the danger happens and the faster the hearing loss happens. So when I tell you guys, hey, turn down your music, you're going deaf, I'm not just saying it because I'm, an old person and I don't want you guys to listen to your music. I'm doing it because there is evidence that shows, hey, when you listen to music that loudly, you physically damage your ears. It will stop you from being able to hear even more than you would normally lose just as you get older. So painful things like a car stereo that you can hear outside the car. Imagine being in it. Jackhammers, firearms or air raid sirens or jets. A metal concert, being right up there next to the big amps. Also, hey, just a hint. Amps, amplitude, makes it louder. All right, yeah, I know, bad joke. All right, so the last thing we're going to talk about here is the speed of sound in different things. So just like we have the different loudness of sound, the sound also has a speed, how fast it can go through stuff. So if we look here, I have just some numbers. They on average go up, but you guys can kind of see here as we go through. So to go through rubber, sound is actually pretty slow when it goes through rubber. It's pretty good at holding sound in. Okay? Air, warm air at 40 degrees Celsius. This is 355. You guys can see that it's actually a little bit faster than when the air is just normal room temperature. So remember I talked about how 20 degrees Celsius, when we did our thermal energy notes, 20 degrees Celsius is about room temperature, about 70 some degrees. Okay? So warmer air actually has faster sound. Things like lead, gold, those metals, they have the speed of sound goes even faster through them. This has to do with how easily the molecules hit each other. So when we looked at, let's bring it back here. When we looked at our molecules here, if they're closer together, they're going to be able to hit each other better. If they're farther apart, that's going to be more difficult. So when we look here at air, we can actually see that air is slower than metals. Okay? It's faster than rubber because rubber doesn't like to move at all, but it's faster in air, or it's faster in metals than it is in air because those molecules can bump into one another. So same thing with glass. Glass is even faster, but copper, which has very conductive molecules, and aluminum, which has very conductive molecules, make things go through them very quick. This is also why we use things like copper and aluminum for our electronics, because they conduct not only sound energy through them, but electrical energy through them very well. Okay, so I lied. This is actually the last thing, and it's mostly for fun. So I wanted you guys to see this image of a tuning fork in some water. So the tuning fork is upside down, the vibrating ends of it are in the water, and you can see how it's making the water move. So if you guys had to guess, would you say this is kinetic energy or potential energy? Yeah, it's kinetic. So it's kinetic because kinetic energy is the energy of moving, right? So we can even see here that the tines of the tuning fork move. They hit the water, making them move. Okay, that sound energy reacts to the water and it makes mechanical energy. Okay, a kinetic energy. So when we look at sound isn't just something we hear. You can also, like, if somebody's blaring their speakers, you could put your hand to the wall and you can feel it. I would suggest everybody try at least once, hold an empty cup and like make noise into it. You're going to be able to feel the sound energy that is getting passed from your voice to that cup. One last thing on that note that is super duper awesome is go to the YouTube link in the description for a seriously cool sound demonstration. It is a guy who is messing around with this idea of sound energy being in different forms, okay? He uses some really awesome stuff, and the song is pretty dope too. So yeah, go to the link to enjoy something that is freaking awesome. I guess this is where the point in the video, according to YouTube, that I'm supposed to go like and subscribe, but I have no idea if I'm even going to allow that. So, stay safe, stay home, keep yourselves taken care of. Alright, I'll talk to you guys later.